In this final video, what we're going to do is we're going to utilize MATLAB to be able to solve ordinary differential equations. So my aim is to show you how to solve first order, a second order, a system, and then also to use the ODE 45 function to be able to approximate solutions numerically. So let's say for some reason that we want to solve a first order differential analytically using MATLAB. So I'm going to clear all, I'm going to CLC, and I'm going to close all, just because in earlier programs we were working with opening and closing files. So the first thing I'm going to do is I'm going to define a symbolic variable, and I'm going to call that y of t. Right? I'm also going to define another one, sol, although we don't need to define the solution. And then I'm going to define now the differential equation. So I'm going to call it EQU, and EQU is going to be equal to, now the problem that we're working on is to solve y prime plus y is equal to sine of t. And I meant to comment that out. So what I'm going to do is I'm just going to rewrite this and solve for y prime and say that y prime equals sine of t minus y, just to make it a little bit easier. To define y prime, I'm going to say that's the derivative of y with respect to t. Right? So this diff yt represents our y prime, and that's going to be equal to the sine of t minus y. So that's our differential. We're going to define some initial conditions. Okay, so I think the initial condition that I gave was that y at 0 is going to be equal to, let's just say 1. And so I'm going to say that condition is going to be y at 0 double equals 1. Okay, so that's our initial condition. And then let's do two things. So we're going to desolve, and we're going to first of all just desolve EQU. So let's see what that does if I execute that. And that gives us the analytic solution, the general solution. And we notice it's general because we have this C3 in there. So that's our family of functions. If I add a second parameter, and I call that COND, and I run it, we'll see that that C3 goes away. And now C3 is replaced with 3/2. So that's how we can utilize MATLAB to be able to solve our differential. If we wanted to, we can say sol is equal to this, and then we could substitute a value back in. So we could say substitute into sol. We're going to substitute for t, and we can substitute any value. I'll just say 5. And what that'll give us is that'll give us the exact value at 5. All right, so notice where we had t before, now it's replaced with 5. All right, so that's a way that we can utilize MATLAB to be able to get specific stuff done with our differential. So that's a first order. Now let's say we want to solve a second order differential equation. It's very similar. So the one that I think I had, so we're going to solve a pretty easy one. Y double prime plus 2y prime plus y is going to be equal to 0. And the initial condition we have is y at 0 is 2, and y prime at 0 is equal to 1. All right, so we're going to do almost everything the same. All right, so we're going to start, and where it's really going to be different is where we start to set up this equation. So the equation now, we're going to say diff yt comma 2. This represents the second derivative. All right, so we're going to say plus 2y prime, so that's diff y comma t, plus y, which is just y of t in this case, is going to be equal to 0. All right, so pay attention to this syntax, because that's how we're going to model our second order differential, or assign it to equation in MATLAB. We're going to have an array of conditions. All right, so let's define another function, or not a function, but a variable. Let's call it dy, and that's going to be the derivative of y with respect to t. And so now what we can do is we can get our conditions. So our conditions, unlike before, where we just had a singular condition, is going to be a matrix of conditions. So that's going to be y at 0 is equal to 2. Right? So that's this one right here. And then we need the derivative, so we're going to say dy at 0 is equal to 1. And remember, dy is just going to be equal to the derivative. So all we're doing is we're just instantiating the derivative at this point at 0. Right? So those are our conditions. Now we're going to solve it in two ways. Let's just solve it without the conditions. Right? So I'm going to solve it, and we should get the general solution. It's going to be a pretty easy solution because we have a pretty easy differential. And notice that because we have repeated roots of -1 for the characteristic equation, if we were to solve it, we get c3 e to the minus t, c4 t e to the minus t. Right? If we wanted to use the initial conditions, just like we did before, we have a second parameter, which we're going to call cond. And cond is just defined right here. We're going to execute. And remember the c3 and the c4. Those are going to go away. Those are replaced with 2 and 3 respectively. If we wanted to substitute and find a specific value, we could use the command that we looked at earlier. So this would just substitute 5 back in. Not surprisingly, it's just going to be 2e, or it's going to be the 2 and the -3. And then we multiply that 3 by 5. So that's how we get this 17 in there. All right, so that's how we can analytically solve just ordinary differentials, first order, second order. If you wanted to go up to a third or fourth order, you could certainly do that. If we want to solve a system, okay, so the system that I had was x prime is going to be equal to 3x plus 4y, and then we had y prime is equal to minus 4y plus 3x. So that's the one that we want to solve. We'll get to initial conditions later. All right, so I'm going to define x of t, y of t, and sol, right, because we have to have those as sims. And I'm going to create two ordinary differential equations. So let's just call the first one, I'll call it ODE1 because it's the first ordinary differential equation. That's going to be equal to diff of x, so that's our derivative, and that's going to be equal to 3x plus 4y. So that's going to be 3 times x plus 4 times y. We're going to define a second ODE. We'll call that ODE2. So that's going to be diff of y, and that's going to be equal to our minus 4x plus 3y. As you can imagine, we're going to create a system of differentials. So let's just call it, I'll call it ordinary differential system, ODES, and that's going to be equal to ODE1 semicolon, not space or not comma, because we want two different lines for this. So we're going to do semicolon ODE2. So be careful with that when you're using your syntax. All right. And let me just go ahead and I'm going to use the dsolve on ODES just to show you what this does at this point. And I'm going to get rid of all this stuff for now. And let's see what happens. And I'm going to leave this intentionally unsuppressed, just so you can get an idea of what's going on behind the scenes at this point. All right, so two things to note. Clearly, ODES at t, which is the default variable in this case, because we defined x and y at t, up here as sims, we get this system of equations, okay? Not surprisingly, that's what we defined it as. And the answer is stored in a struct. And a struct is basically a multiple record sort of array. All right, so basically we would have to access those records. So if we want to access the records, just like we would in most programming languages, we're going to use a variable. Now I'm going to define S to be the D solve, and what I'm going to say is S dot X and S dot Y. Now I'm going to assign these to variables in a moment, but let me show you what happens when you do S dot X and S dot Y. Okay, we get the answers. Right? So these are our answers, and the dot just accesses the variable of the X. Okay, so that's going to access the first variable with respect to X, and then it's going to access the second variable, which was with respect to Y. Right? Now we can define some functions, or not even functions, but we can just find some variables to assume these in terms of t. So I'm going to call one the X sol in terms of t, and I'm going to suppress that when I'm done. And I'm going to call the Y sol in terms of t is equal to Sx and Sy. All right, so now we have variables. All right, and if I was to execute it again, it would do the same thing. It's not going to do anything different, except now we have them defined as X and Y sol. All right, so that's how we can solve for the general solution. So what if we want a particular solution? Well, not surprisingly, just like we did before with the second order differential, we're going to have to construct a system. And we're going to be careful when we construct, a matrix. So let's just say for some reason condition 1 is going to be equal to x at 0 is equal to 1. And let's say our second condition, condition 2, is going to be equal to y at 0 is going to be equal to 2 for some reason. All right, so those are our initial conditions. Now be careful with this. I'm going to say condition is going to be equal to cond 1, cond 2. All right, and as you can imagine, we're probably going to get an error for this. So let me go ahead and execute this. All right, and it tells us what the condition is. Okay, well, I didn't do anything with it because I didn't do the D solve. So let me go back down and let me copy this. All right, there we go. All right, so now we have D solve and we have the ODEs of the conditions. All right, so let me go ahead and execute this, and we're probably going to get an error, and we can fix that error very easily. All right, so we have a struct. All right, we have our condition, but unfortunately, if we try to access that, it's not going to work out for us too well. The reason it's not going to work out is because we need a semicolon, because we need to go to the next line. All right, so if I execute it, S is probably still going to be a struct, all right, which it is. All right. So we can assign this to be an array if we really wanted to. All right, so, and this should be cond. Okay, so that's good. So let's do this. Let's define this to be an array. So let's call this, I think we called it X sol initially. So this is X sol of t and Y sol of t. So we're just going to reuse those variables. And we're going to store them into an array, this time with a comma. All right, so now we just have a 1 by 2 array, and we can execute this, and we don't need the struct any longer. Or we shouldn't. Okay, so here we are. So now we get the particular solution. If we wanted to, we could plot these on the same graph. We could see points of intersection, all kinds of good stuff that we want to do with this. All right, so this is probably the easiest way that I can think of to be able to solve a system of differentials. So we did have to use a couple new data structures like this struct accessing the records, and then we had to use a 2 by 1 or a 1 by 2 and then a 2 by 1 to be able, or arrays to be able to access this, but not too bad. Right. Now the last thing I want to show you is how to approximate a solution using the ODE45 function. All right, so let me get rid of all this, well, most of this. Unfortunately, to do this, we're going to have to create a function. All right, so let me get rid of all this stuff. And I'm going to create a new tab. And I'm going to call this function f is going to be equal to, let's say, my function, I'll call it my fun1. and that's going to have two variables, a y and a t, or a t and a y, excuse me. All right. And let's say we wanted to solve, so here's the problem that we're trying to accomplish. We want to solve y prime plus y is equal to sine of t. Remember we had y at 0 was equal to 1, and let's approximate y at 5. All right, so that's the problem that we're trying to solve, and we want to use ODE 45 to be able to do this. Of course, we could do this analytically. All right, so we have function f equals my fun, and let's say f, which is the function, is going to be equal to sine of t minus y. All right, now I have to save this as a function, so I'm going to save, and I'm just going to save this as my fun 1. So I'll save it, and I want you to notice what happens. Over here, this comes up not as a .m file, well it is a .m file, but it has the special graphic that it's a function. All right. So down here in the command window, we're going to call the function, and we're going to store it. So we're going to say xy, which is an array, and I'll show you in a moment what that's going to do for us, is going to be equal to, here's the function ODE 45. We're going to call my fun 1. Okay, so that's the function that we're looking at. We're going to start at 0 because 0 is the initial condition. Right? We're going to go all the way up to 5 because that's what we want to predict, y of 5. And then the initial condition for y is 1. So remember, y at 0 is 1. So this is the span for t, the independent variable, and this is going to be the initial condition of the dependent variable. Right. So let's see what this does after we execute it. And it does a couple things very nicely. I should have suppressed that function, but what it's doing is it's telling us all the x values, or in this case the t values. I probably should have said t comma y, but that's okay. So these are the increments of the steps. All right, and that's what the ODE 45 function does. Very similar to Euler's method or to a Runge-Kutta method. It just has not necessarily consistent steps, but it does have steps. And then these are each of the values. So this is the initial condition, and then this is y after step 1, y after iteration 2, etc. And eventually what we get to is this negative 0.6112. All right, so let's hold on to that value. And let's see if we were to go through and get the exact solution, if that's what it would give us. All right, so I'm going to go back here. I'm going to CLC, I'm going to clear all, and I am going to close all. I'm going to have a sims of y at t. And then let's just go ahead and solve this. So we're going to say EQU is going to be equal to diff y comma t. That's going to be equal to sine of t minus y, suppressed. Our condition is that y at 0 is equal to 1, which was our initial condition. And then finally we're going to desolve EQU comma cond. All right, now I am going to put this comment in here that ODE 45 gave negative 0.6112. Right? And we do need to substitute, so let's just call this sol, and I should probably make that a symbolic variable so we can do the substitution. And we are going to substitute into sol for t, and we're going to substitute 5. Okay. So remember, ODE 45 gave us this number, so we're going to go ahead and execute this. Right here should be a double equal. You're probably all screaming at me about that. All right. It gives us the exact answer. So let me format that into a floating point, so we'll do an fprintf, and we'll have %f. All right, and we're going to say I'm going to define this as, I'll just define it as p. All right, so let's try one more time. All right, and check this out. We got negative 0.611186. ODE 45 gave us negative 0.6112, so they're both extremely close to one another. And the good news is with ODE 45, we were able to approximate that very easily with a lot less code. This works very well with differentials that do not have analytic solutions. So hopefully this gives you a good idea as to how to utilize MATLAB to be able to solve various types of differentials, both analytically as well as numerically.